Okay, 10 a.m. Let's get going. While we're waiting for tribute to show up, we'll go through and summarize where we left off. So we're working with a whole collection of vectors instead of just looking at ax equals b now. So we have Rn is all possible n by 1 column vectors where the entries of the vectors are just real numbers. So we identify Rn with column vectors, and hence we just call the elements of Rn vectors in general. Then we're looking at some of the algebraic properties, and we said that a vector v in Rn is a linear combination of a finite set of vectors in Rm that we denote by v1 up to vm, if we can find scalars alpha 1, alpha 2, alpha m in R that solve the equation v equals alpha 1 v1 plus alpha 2 v2 dot 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 alpha m vm. Okay, so this is writing v as a linear combination of v1 to vm. So linear sum, and then m finite. So we can use that concept to talk about whether ax equals b has a solution, and we don't care whether a is square, rectangular, etc. And the result is ax equals b has a solution if and only if b can be written as a linear combination of the columns of A. And you just do that by writing A in its columns, breaking X into its components, and then you use column times row, and the rows of this are trivial, they're just real numbers. And so I take those real numbers, which would normally be sitting here, and I just move them over, and I get B is a linear combination of the columns of A. And that's exactly the same thing. Okay, so that gives us a necessary and sufficient condition for solutions, and we don't need to worry about whether A is square or not. And then we just got started with linear independence at the very end of lecture. And we'll see that this ties into uniqueness of solutions of equations, and we don't care whether A is rectangular or square or not. Okay, so we take a finite set of vectors in Rn, we say they are independent, more precisely linearly independent, if whenever I form a linear combination from them, the only way they all add up to 0 is if all the coefficients are 0. Okay, so this is saying really the unique solution to this equation is this vector equals the 0 vector. Another way to say it. Linear independence, I cannot write V1, for example, as a linear combination of the others. And what we had noted at the very end of lecture was, suppose one of these coefficients is non-zero. You know, maybe it's a middle one here. Relabel it and now assume alpha 1 is non-zero. Then I can just move all of the other vectors to the other side and then divide by alpha 1, and then I would have written V1 as a linear combination of the others. So that would say I could generate V1 by just doing simple operations on these, and hence this vector wouldn't be useful. I can get it other ways. That's why it's not independent. It depends on the others. So if vectors are independent and you're trying to generate vectors through linear combinations, then you can't throw them away. That's where the independence comes. So today we're going to go through how you check it. You're going to see that the definition, applying it, is super painful. And then we're going to be motivated to look at a pro tip. How do the pros do it, okay? And then if there's time, we'll go through the proof, and I want to go through it either at the end of class today or on Friday. So let's do our first example and see if we can make sense of these definitions. Okay, so is set, the set, and I'll use our special unit vectors. Whoops, E3 equals 0, 0, 1, linearly independent in R3. Okay, so we're just making sure that we've got the definition down. So how do we do it? How do we do it? So we take alpha, we have three vectors. We take alpha 1, alpha 2, alpha 3, three real numbers. And we seek a solution to alpha 1 times E1 plus alpha 2 times E2 plus alpha 3 times E3 equals the 0 vector in R3. Okay, let you catch up, write that down. Okay, so these vectors are particularly nice because when we add these up, all we get is, we do the first row, we get alpha 1, we do the second row, we get alpha 2, we do the third row, we get alpha 3, 0, 0, 0. So there's only one solution to this equation. So there's only one solution, and it's alpha 1 equals alpha 2 equals alpha 3 equals 0. And that's what we mean by linear independence. So these vectors, this set of vectors is linearly independent. Okay, so that one's kind of trivial. Okay, I don't know. We'll call this example A. Call this example B. So, is the set of vectors, now I'll call them V1, V2, V3, and I'll do 1, 1, V2 super complicated 2, 3, and then V3, 1, 2. Is this set linearly independent? Okay. Well, let's just observe instead of writing down all the equations on this one. Can I write one of the vectors as a linear combination of the others? So look at V3. And if you're confused about what those numbers are, I get it. 1 and 2, okay? Can I write V3 as a linear combination of V1 and V2? And it's just equal to V2 minus V1. Okay, so conclusion. If I just then write this out, I have minus V1 plus V2 minus V3 equals the 0 vector in R2. And so these vectors are linearly dependent. So, just to be super overkill on this one, I'm looking for alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 equals 0. Is there a non-trivial solution to this equation? Okay, you get that? And then let's see if we can write down one solution. So here's alpha 1 minus 1, here's alpha 2 plus 1, here's alpha 3 minus 1. Okay, so there's a solution that's non-trivial. So minus 1, alpha 2 equals 1, alpha 3 equals minus 1. Okay, but as soon as we have this, we can stop here. We don't have to do anything more, because this already says they're not independent because one of them can be written as a linear combination of the others. And if you're linearly independent, that does not happen, cannot happen. Okay? So that's what's going on here. So it's just overkill to go ahead and do it. Once you have that, you can always pop out the coefficients. So let's do one that's a little bit less trivial. So example C. And then we'll do example D that is just going to push us over the edge and try to make us do something else, okay? So is the set of vectors now, V1 has 3 components, wisely selected. V2 also has 3 components, more or less randomly selected. Is this set of vectors linearly independent? Okay, so we're going to apply the definition. Just like we did with E1 and E2. So we seek alpha 1, alpha 2 real numbers such that we want to take alpha 1 times v1, alpha 2 times v2. And so that's alpha 1, and my vector was 1, 2, 3, plus alpha 2, and my other vector was 1 minus 2, 4. And let's go ahead and add those up, and then we'll write down 0, 0, 0. So this gives us alpha 1 plus alpha 2, right? The first row. Second row is going to be 2 alpha 1 minus 2 alpha 2, and then 3 alpha 1 and 4 alpha 2. So let's just write that down. 2 alpha 1 minus 2 alpha 2, 3 alpha 1 plus 4 alpha 2, and we need to get the 0 vector in R3. Okay, so that's what we have to do when we apply the definition. So how do we go about solving that set of equations? It's not square. Well, here's one way to do it. We note that if alpha 1 and alpha 2 solve the above 3 equations, then they must also solve the first 2. So that's an arbitrary choice, okay? So I'm just going to reduce it to a square system by taking only the first 2 equations and see what I get. Okay, so the first 2 equations would be alpha 1 plus alpha 2 equals 0. And the second equation is 2 alpha 1 minus 2 alpha 2. Okay. Let me stop and see if the logic is clear on what we've done. Everybody in class here is nodding. Is there questions from the Zoom group? We write down the definition of linear independence. We're checking to see if there's only the 0 solution or maybe there's some other hidden solution to those equations. That's exactly what they are. But if 3 equations are satisfied, then that means the first 2 are also satisfied. And this looks a little bit easier to tackle. So what if we write that as a matrix? 1, 1, 2, minus 2, alpha 1, alpha 2 equals 0, 0. Now, if we can prove that matrix equation has only one solution, what does that solution have to be? Question from...
So the question is, wouldn't the only way to get a non-zero solution if there are infinite solutions?
An infinity of solutions?
Infinite solutions.
Yeah. Mm-hmm. So this was about here? Yeah, so we're looking if there's a non-trivial solution. So if we know 0 is a solution, if we have a set of linear equations and there is one other solution, meaning it's not 0, then there's also an infinite number of other non-trivial solutions. That would be correct, okay? So we only need to find one non-trivial solution to conclude that the vectors are linearly dependent. Or we prove there are no non-trivial solution. The only solution is the 0 vector for alphas. So if I'm looking at this matrix equation and I want to conclude that alpha 1, alpha 2 equals 0 is the only solution, what's the easiest thing to do? So call that A. If I know 0 is a solution and I want it to be the only solution, I want it to be unique. How do I check for a square system of equations if it has a unique answer? The determinant, yes. So we just check determinant of A. And so that's 1 times minus 2 minus 1 times 2. That's minus 4. That's not equal to 0. Conclusion, alpha 1 equals alpha 2 equals 0 is the unique solution. Yes, question?
So why are we only solving for the first two instead of the third row?
So the question is, why did I pick out the first two equations and ignored the third row? Okay, so I'm looking for solutions that satisfy all three of these. If I can find a solution to the first two, I then need to verify that it also satisfies the third one for it to be a solution to all three equations. Okay, I could have picked this one and this one, the first and third row, and solved that, and then take that solution and plug it back into here. So I do need to solve all three. Now, look, we note though that 0 is always a solution to getting 0. So there is a common solution to these equations, the trivial solution. The question is, does there exist another one? Is there another one hidden in there? And so if I can take any two of them and show that 0 is the only solution of those, then I'm done. There can't be a third one. That's the logic. And so I just happen to choose the first two, and I would invite you to take this one and this one, the first and third, and you'll change the bottom row here, but you won't change that the determinant is non-zero on that one. Okay, so that's the logic. Find any way I can to assert that alpha 1 equals 0, alpha 2 equals 0 is the unique solution. And so now I can conclude the vectors are linearly independent. Conclusion, linearly independent. Yay. Okay, so it's a little bit painful. I want to make it more painful so that the pro tip becomes amazing. That's all I want, okay? So now I'm going to ask, is the set of vectors V1, 1, 2, 3, 1, comma, V2 equals, what did I do? 0. I don't think I really care what I put here, but I'll use what I have in my notes. 0, minus 2, 4, 5, and then I'll do V3 equals something else. 2, 6, 2, minus 3. Is this set linearly independent? So how do we go about that? It's always the same thing. We have to check if there's three vectors, alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equals the zero vector. Okay, I'm just going to remind you it's a 4 vector, so it has 4 zeros, has a non-trivial solution. Solution or not. So if I can find this non-trivial solution, then it is not linearly independent. And if the only solution is alpha 1, 0, alpha 2, 0, alpha 3, 0, then it is linear, the set is linearly independent. Okay. We can write the matrix equation down immediately because alpha 1 v1, alpha 2 v2, alpha 3 v3 is the same as putting this as a column. Whoops. We put this as a column, this is a column, this is a column. And so I have these things written down here. 1, 2, 3, 1, 0, minus 2, 4, 5, 2, 6, 2, 3, alpha 1, alpha 2, alpha 3 equals 1, 2, 3, 4 zeros. Whew. So this is 4 by 3, this is 3 by 1, so this has to be 4 by 1. It all checks, okay? Okay, so we could solve this, but we would not enjoy it. Everybody agree with that? If we have a plurality of people who want to go through the solution and grind it out, we could do it, but I don't think anybody really wants to do it, okay? There has to be a better way. Right? There has to be a better way. This would never scale to 27 vectors and checking if it's linearly independent. It would just drive you crazy, okay? There has to be a better way. Okay? Okay, so here's the pro tip. Okay, so this is how the pros check this. How to check linear independence like a pro. Okay, so we're going to be given a set of vectors, and I'm going to do it in general. And for some funny reason, I'm going to label these vectors just like they're the columns of a matrix. Why? Because any finite collection of vectors in Rn, I can always stack them up as the columns of a matrix. We've talked about that going back and forth there. So this would be A11, and then the second row in the first column, dot, 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 the last row in the first column. And then my second vector, you know, those are just numbers. 11,419 square root of pi e to the power 100. They're just numbers. Okay, so then this would be still the first row and the second column and the second row and the second column, dot, dot, dot. Last row and the second column. And then VM, it's still the first row and it's the mth column, the second row and the mth column, dot, 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 nth row, mth column. So we're going to go back and apply this to our example that we thought was too painful eventually. Okay, so everybody good? We have m vectors. We gave them some names for the elements, and that's all we've done here, okay? Oh, I can see interest picking up a little bit. Finally, I've got you hooked on something. So guess how I'm going to define my matrix A. It's going to be the first column is V1, the second column is V2, the last column is VM. And yeah, and now I'm happier writing my matrices by rows. I don't know about you guys, okay, but that's what I like to do. Dot, 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 AN1, AN2, dot, 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 ANM. Okay, N by M. So these are vectors in Rn. They have n components, and we have m of them. So n rows, m columns. Okay, that's it. Okay, so pro tip, shove immediately all your vectors into A. Then the result is then V1, V2, dot, 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 VM is linearly independent if and only if the determinant of A transpose times A is not equal to 0. Ooh. Okay, shove all of our vectors into the column of a matrix. That's probably where they came from anyway, okay? But if we're just given these stray vectors lying around, we just form them up into the column, and we form A transpose times A. So let's just note A transpose times A. Well, A is n by m, so A transpose is m by n times n by m, and so that's now square. So that's why we can take its determinant, okay? And then the proof of this pro tip to come end of today or Friday. Because I want you to understand why this is true. I won't hold you accountable for the proofs, but we can't have all of this seeming like black magic all the time, okay? And the reasoning is very linear. It's very linear reasoning. So I think you will enjoy why it's there. So let's just redo some examples now with the pro tip. So we'll redo example C. You don't remember the vectors, but I've got them written down. 1, 2, 3. V2 is 1 minus 2, 4. Well, first thing we do is we shove those things into a matrix. 1, 2, 3, 1 minus 2, 4. So in Julia, if I give you 5 or 6 vectors, boom, 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 you just list them out, put them in the columns. Then we form A transpose times A. Okay, what does A transpose do? It takes the rows and you put them as columns. So I'll write it out just so you remember what it is. Take the first row, you make the first column. Take the second row and you get the second column. You take the third row and you get the third column. Okay, and then once again, so this was 3 by 2, this is 2 by 3, 3 by 2, so we have to get a 2 by 2, and I don't think you guys need me to go through the matrix multiplication. You'll work that out at home, or you'll just say, I don't care. Okay, so that's 2 by 2. And so that's 14 times 21 minus 15 squared. If you want to put a minus sign in there, it doesn't matter. And that's 69, and it's not equal to 0. Okay, that matrix is not equal to 0, and so we conclude linear vectors are linearly independent. Hey. Okay, let you catch up on the writing. We'll go back and just show what a shortcut this really is. And then the next example, you're going to be like completely blown away and walking out feeling like, yay, we finally did something useful in Rob 101. Okay, so let's go back to example C. We took these vectors, we formed the linear combination, we got 3 equations and 2 unknowns, and we just set about trying to solve those equations, okay? Yes, we can do that, okay? Here, if this is really true, you know, whoops, we just took the vectors, shoved them into the matrix, formed a square matrix out of it by doing A transpose A, and then we calculated a determinant. When you write it like this, it seems, oh my gosh, that looks really complicated. But when you write it out, that's a 2 by 2 matrix, and you're going like, no problem. Okay, so this could be 2 vectors in R17, and you still get a 2 by 2 matrix that you check the determinant of, okay? So that makes that seem really easy. Questions before we do my coup de grace? Yes?
The minus 15 in there should be 9, the multiplication.
Where?
The 14 minus 15, instead of that should be 9.
14 times 21 minus 15 squared is minus 69?
No, the step before in the multiplication. So one, the first column and the second, the first row and the second column.
1, 1, 2 minus 2, 3. I'm confused.
So 1, 1 is 1, and then minus 4 minus 3, and then 4 times 3 is 12, so 9 minus 3 is...
Oh, you're saying these numbers here are wrong. Yeah, okay. Okay, I'll clean that up when I post it. Yeah. Okay. Let's do example D. Okay, so this is the one we didn't have the heart to really go through. Okay, so let's do this example, and I'm just going to paste it in and so we can walk through it. So just make a note that you can copy it out of images, example D, yay. Okay, so here's the three vectors that we had. V1, V2, V3. We just put them into the columns of A. We go to Julia and we calculate A transpose A. So that's 3 by 3, right? So how do we do the determinant of a 3 by 3 matrix? Or a 9 by 9 matrix, or a 20 by 20 matrix, okay? We just do the LU factorization, and we use the fact that the determinant of a product is the product of the determinants. So we've talked about this, how LU reduces everything down. Okay, so we get that the determinant of A transpose A is the determinant of P times the determinant of L times the determinant of U. But remember that this is a permutation matrix. Its determinant is always equal to plus or minus 1. So it can never cause a 0. That's the whole thing about permutation matrices. L always has 1s on its diagonal. Its determinant is just 1. So the only place we can get this thing having a non-zero determinant, so there's a non-unique solution to our equation, is if U has a 0 determinant. So we simply look on its diagonal, and I've boxed in where the 0 is. Okay? So, determinant of A transpose A is equal to 0 if and only if U has a 0 on its diagonal. Okay, so that's our method for getting the determinant of anything that's bigger than 2 by 2. You just do the LU factorization and we look at this, and so we get to conclude immediately the vectors V1, V2, and V3 are linearly dependent. How about that? Clean. We just use the tools that we've developed so far in the course with this one pro tip trick. You want to think about it that way? I'll show you it's not a trick. There's plenty of logic behind it. But the magic is forming up A and then forming, whoops, I keep doing that. Come on, there we go. forming A transpose A, we get a square matrix. And what you want to understand eventually is why does this matrix, being invertible or not, determine whether, because we're really solving A alpha equals 0, 0, 0, 0. Why does A transpose A, being non-singular, having a determinant that's not equal to 0, tell you whether there is or is not a non-trivial solution here? Okay, that's interesting. We're going to start that. But let's make sure we know how to apply the pro tip. We form up the vectors into the matrix. A transpose A, we take its determinant, and the way we do determinants is LU factorization if it's bigger than 2 by 2. Are we good with the idea there? Okay, so everybody knows how to check linear independence now and make it a trivial calculation in Julia with the tools that you have. So why is this true then? Okay, why is the pro tip true? And I don't think I'll get the whole thing today, but pretty close. What's the secret sauce, okay? Okay, so each step is going to be really small, but they're all going to add up to this kind of amazing thing. So let y be a vector, and it has n components. I don't really care. Could be k, but it has n. Okay, so this is in Rn. What do I get if I form y transpose times y? So I'm just going to write out y transpose. That gives me a row vector. I have my original y. Okay. Okay, so I want to multiply this. So I take this one times this one. That's y1 squared. I add it to this one times this one. That's y2 squared. And then I add dot, 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 this one times this one. That's yn squared. So it's y1 squared plus y2 squared plus dot, 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 yn squared. So I claim y is equal to the 0 vector if and only if then y transpose times y is equal to the 0 scalar. Okay? It's a little simple observation. It's going to have big importance. Let's see if we agree this is true. The only way this thing adds up to 0 is if every single one of these elements are 0. That's absolutely, positively true. If y14 is 0.1, okay, and I square it, I still get something that's not 0, okay? So this is equal to 0 if and only if this is equal to 0. Okay. So we are looking for non-trivial solutions to the matrix equation A times alpha equals 0. Okay, and this is the 0 in Rn. That's n by 1. A was n by m, and alpha is m by 1. Okay. I just ran out of time, so I'll write this down and stop. So we let A is this, and stay tuned. Come back next Friday for the concluding episode of Why is this pro tip going to work, okay? Oh, leaving you in a bind there. So why don't you play with it yourself, see if you can derive it if you want. You're not responsible for the proof. A proof will never show up on a homework or a quiz. This is just for our satisfaction that this is not all black magic, okay? We're just throwing them in every once in a while to show that, yay, there's something behind this stuff that we're doing. So thank you for your attention.